Thank you. Thank you, everyone, for coming. We're here to talk about eBPF and Kubernetes, and specifically the Tetragon project, which we'll introduce in a moment. First of all, a little bit about us. Anna, would you like to introduce yourself?
Sure. Hi, everyone. I'm Anna. I work at Observability as a software engineer on everything observability related, our observability products, things like Grafana integrations too. I spoke here last year about network observability with Cilium and Hubble. And in my previous life, I also did a bit of astronomy outreach. So if anybody would like to talk to me about galaxies and exoplanets, then feel free to find me.
Cool. Hi, my name is James Laverack. I am a senior solutions architect at Isovalent. I have worked upstream in the Kubernetes project. I've formerly been a release lead for Kubernetes 124. I also spoke here last year about TLS certificates with the In Clouds We Trust talk. And I'm a weird board game nerd. So there you go. All right. So what we're going to talk about today is we're going to talk about Tetragon. So we're going to talk about the kind of problems it is designed to solve. We're going to talk a little bit about eBPF, which is something that Liz talked about earlier and has been mentioned a couple of times. And then we're going to talk about how Tetragon uses eBPF to solve these problems. So let's start by talking about the Kubernetes side of things, so Kubernetes in general. And security in Kubernetes is an extremely deep topic. There are lots of talks about it. There are lots of things to know. There are lots of detail to get into. But Tetragon specifically focuses on three main things, which is security policies, runtime enforcement, and monitoring and observability. So all the rest of that stuff is outside of Tetragon's scope. It's not designed to be a catch-all, everything security tool. Few facts about it. It's open source, Apache 2 and GNU GPL, depending on the part of the code you're looking at. It is part of the Cilium project, which has just graduated, and so this is part of the CNCF and fully open source and open governance. And as we're going to mention, it's powered by eBPF. This is an extremely high-level architecture diagram. I'm not going to dwell on this too long, but this is the general idea of how it works. There is an agent that runs inside your cluster in Kubernetes, which installs eBPF programs to instrument parts, the things that the kernel is doing, syscalls mostly, but all kinds of stuff. The other big thing to know about it is that there's no need to specifically instrument your code. It does not require you to recompile anything. Because this works in the kernel, it also doesn't require you to use any particular language. This will work just as well on a compiled, statically linked Go binary as it will a fully interpreted Clojure program in the JVM. It's all the same thing to it. And it's fully Kubernetes native. So that means it has awareness for what a pod is. It has awareness for what a namespace is, which are things that the kernel by itself does not know about. And it can enrich the information that comes out of the events that you'll see from it, which you'll see later, using all of this information from Kubernetes to really help tie it all together. We're going to focus on three main use cases. We're going to talk about process lifecycle and seeing what your processes in your cluster are up to. We're going to talk about network visibility, including if you don't use Cilium as your CNI. Tetragon does not require Cilium running in the same cluster, but of course it does work well with it. And we're going to talk about file operations, so weird things in containers opening files that they shouldn't. Anna, do you want to talk about the complicated eBPF bit?
Sure. So eBPF. I'm sure most of you heard that word many times even today, but I assume not everybody might be super familiar with eBPF. So I will start with a quick introduction of what it is, what it can do for us. So eBPF stands for Extended Berkeley Packet Filter, and forget about it, honestly. Naming things is hard. It can do so much more than packet filtering. eBPF is a technology that allows us to extend the Linux kernel with custom programs. So we can load custom code, for example, monitoring applications to run in the kernel space. There's no need to instrument the applications or even restart them to actually enhance them with eBPF programs. And this also gives us very little overhead of, for example, monitoring applications, because we run things efficiently in the kernel and we save on all this communication between the kernel and the user space. This whole concept of extending Linux kernel is not exactly new. It's also possible with kernel modules. However, writing kernel modules is difficult. It's full-on kernel programming. And if a kernel module crashes, then it crashes the whole machine. That's why people have been very, very careful with loading kernel modules. With eBPF, we don't have this concern because a very interesting piece of software that is the verifier. The eBPF verifier that checks every single eBPF program that it's safe to run, that is that it won't loop forever, that it won't access memory, that it shouldn't access things like that. And eBPF programs are written in C, usually, and then they are attached to a hook point inside Linux kernel. So here's a picture how it works in more details. First, some kind of agent, for example, Tetragon, loads an eBPF program to the kernel using a BPF syscall. Then verifier checks that the program is safe to run. Then just-in-time compiler compiles the program, makes it fast. And after that, our application, written in whatever language, doing whatever we need it to do, just does its job. Whenever it needs to, for example, do a network call, read a file, do anything useful, really, it needs to reach to the kernel to access underlying hardware. And when we execute things in the kernel, if our eBPF program is attached to certain hook points, then it just gets executed on every execution of this hook point. So I mentioned these hook points in a kernel a few times. What are they exactly? Here's a sneak peek of Tetragon configuration. Tetragon is designed in a way to be very flexible. So it allows you to attach and monitor literally whatever in the Linux kernel. One of the most popular hook points are kprobes, so kernel probes. These are functions in the Linux kernel, simple functions. We can just attach to them. There are also kret probes, like kprobes, but they are executed on return of the function, not when it starts, but when it returns, so we have access to return value, thanks to that. There are also trace points, which are more statically defined hook points, more stable than kprobes. There are uprobes, uret probes, like kprobes again, but for user space functions. And there are a few other hook points, some added in newer versions of the kernel, but these are the most important ones for observability use cases. So we can monitor all these kernel functions in eBPF, but this is not observability. To actually improve application observability, we need to have some context in the data we produce, some business context, and we need to correlate these different things that are happening. And eBPF has a way to do that, BPF maps. So any computer program actually has to have some sort of state to do useful things. This can be a database, a cache in regular user space applications. In eBPF, these are BPF maps. There are a few kinds of them, like hash tables, ring buffer, etc. These are all basically key value stores stored in the kernel memory. And this is a feature that actually makes BPF useful for observability. So first of all, we can use BPF maps to pass high-level context from user space to the kernel. For example, pass Kubernetes metadata in this way. And we will show an example later, but we can really pass any business context we need. Secondly, we can correlate between different hook points. So different eBPF programs can store their state in the same BPF map. And then we can correlate, for example, what happens during a process execution and what happens when this process reads a file. Thanks to that, we actually produce not just some output, whatever is going on in the kernel, but we produce actual useful information about the behavior of the application. And of course, if you produce data, user has to somehow read them. So we also use BPF maps to pass data from the kernel to user space, so user can read this data and use them. All right. So with that, this was a quick intro to eBPF. Let's move on to actually useful stuff. So what Tetragon is useful for.
All right. Thank you, Anna. Thank you. First thing we're going to talk about is process execution. So what processes do. As you are all probably, hopefully aware, most containers contain processes and actually are just processes with extra sugar on top. And no one wants to run these in a particularly privileged mode, right? Like, no one wants to do that. But the truth is that we do. We need to for various things. Cilium, a great example, as a CNI, needs access to the host network namespace. You often need to use various Linux capabilities, such as catnetadmin and capsysadmin, and you need high levels of privilege to load eBPF programs in the first place. So there are lots of reasons why you need to be able to do this. Kubernetes, of course, does have some management and interaction with capabilities built in. There is the concept these days of pod security admission, which you should totally use in your clusters, by the way, which is a kind of Kubernetes native way of managing high levels of access within your Kubernetes clusters. But how Tetragon can help is it can let you see what is actually going on, even in those privileged pods. So let's take an example. We're going to enable so we're going to take a cluster where we've already got Tetragon involved. I'm not actually going to do a demo. I'm not as brave as others. I'm going to talk you through how to do this. So by default, Tetragon doesn't expose this information, but we can turn it on using configuration. So in the first line, I'm going to modify its configuration in the config map. And then in the second line, I'm going to restart Tetragon in order to pick up the new config. So once I've done that, we can start seeing what we can see. So I'm going to deploy a pod. And the pod I'm going to deploy is extremely simple. It's just going to go to sleep, but it's running with security context privilege true. So this is the classic way of getting higher levels of permission in processes within your Kubernetes cluster. And once I've run it, I am going to look at the Tetragon output events. So what I'm doing here is I'm getting the logs from the Tetragon pods, and specifically the export stood out container, and I'm following them. That container is a special extra container in part of Tetragon that will output all the events as JSON blobs to the log file so you can see them more easily. And then there's a local command line utility called Tetra, which allows you to parse that into a slightly nicer to see way. So that's what we're going to do. So if I run this in my local cluster, what do I get? Well, I get all of this. Interestingly, I ran this in a kind cluster as a demo. All this stuff that I've annotated with blue is actually kind setup. And that's because kind, as part of its deployment, hooks into the CRI config for containerd. And you can actually see this, which is quite interesting. You can see that it's running a script called kind bin mount product files.sh. And you can see that that runs JQ, that runs copy, that runs, I think it runs mount somewhere, and then the script itself exits. So that's not what we were looking for here, but it's pretty interesting to know that we can see that because it's running within the container. And then right at the bottom, we can see that sleep runs. And we can see on the right there that it has capsysadmin. So we've been able to discover that it has more permissions than it needs because we've been able to view this. So if you saw this in like a real cluster log, you would probably wonder why you're running sleep, but you'd also wonder that this is too much permission, perhaps, for this thing. And to expand on the example, in this, I've done a lovely dirty pipe to JQ, which is how you solve all problems with JSON, where I've just taken all the events, I've piped them through JQ to filter for ones with capsysadmin, and I've put that through Tetra. And now I can see every process running inside of my cluster which has capsysadmin, which is pretty interesting. And you can see how you can use these events from Tetragon to build more information about what's happening in your cluster. But let's talk about the network.
All right, networking. So there is a lot going on the network in typical Kubernetes cluster. There are, of course, applications talking to each other. Usually there is some database, some streaming solution that transfers a lot of data over the network. There are usually some integrations with cloud providers, requests to external SaaS products, some health checks going on in the background. Potentially some attackers. There is also DNS, which could have its own slide, but this is not a talk about DNS, so let's not talk about it more. There's a lot going on the network, and monitoring all of that can be very quickly overwhelming. We know already that eBPF can do that, but it quickly can overwhelm somebody looking at this data. So this is why Tetragon by default doesn't monitor all these things. By default, it monitors only process execution that James just showed in the previous section. Everything else can be monitored, enabled using tracing policy CRD. So let's see some examples of that. Here is an example tracing policy, which defines what hook points we want Tetragon programs to attach to. Here we have 3 hook points, 3 kprobes, TCP connect, TCP close, and TCP send message. So we want to monitor when TCP connections is opened, closed, and when we are transferring data. In tracing policy, we can also define what arguments we want to track, so what data we want to get exactly from these calls. Because Tetragon is deeply integrated with Kubernetes, tracing policies also allow us to filter by Kubernetes metadata. There is also namespace tracing policy CRD, and there is pod selector. So in tracing policy, we can define pod selectors and match only events triggered by pods with specific labels, for example. These filters are actually propagated to BPF. So these filters are stored in BPF maps, and all the filtering happens actually in kernel, in BPF programs. Apart from Kubernetes metadata, there are also other filters. So here we can see an example selector that filters by IP addresses. That kind of filter allows us to filter, for example, only external connections. If we have, for example, an air-gapped cluster and we don't want any external connections, or we want to check that external connections are only known domains, for example, known SaaS product, then it's useful to monitor everything else. All right. So this was a lot of YAM. Let's look at some BPF code too. Are we ready for this? I hope you are. So here is actual Tetragon code. There is a link at the bottom. Tetragon is hosted on GitHub, so if you want to read this in more details, then feel free to. This is actual Tetragon code responsible for filtering IPs. We see here that we are getting the filter we defined in the tracing policy and an IP that we are trying to connect to as arguments to this function. There are some map lookups. So we are checking in a BPF map if this IP that we got is in the range we want to monitor. And depending on the filter, if this filter is allow or exclude, we return the correct value and produce an event or not. All right, so with this tracing policy, if we run free commands, free curls like this, here we see 3 curls. 2 of them are to external domain, eBPF.io. One of them is KCD-UK namespace, another one is another namespace, and another one is also KCD-UK namespace, but curl inside a cluster. With that, we will see an output with tetraget events that contains this connect, close, and send message events. Send message also reports us how many bytes were sent, but we see it only for one of the connections, only for the one that was in KCD-UK namespace and to the external domain, because we defined our tracing policy to catch only these events. All right, so this is how we can monitor networking with Tetragon. Now, apart from networking, programs need to also read a lot of files, so I will hand over to James to talk about this.
All right, so this is our last kind of concrete example. There are lots of other ways to use Tetragon. But I'm going to talk about file name access, or specifically accessing files. This is something that, of course, processors need to do, but a very common operation for an attacker, if they've gotten access to part of your cluster, is going to be to have a look around and see what they can see and try to exfiltrate something interesting. From this, you might be asking, well, doesn't Kubernetes already do this? Doesn't containers already solve this problem? You know, all file system access is sandboxed anyway. You don't give everything read access to everything. And yes, that's true, but not always. Sometimes, especially in older systems that have been lifted and shifted into a container, you have multiple processes in the same pod or the same container. We don't like it, it's ugly, but it works, people do it. And sometimes one of them might be able to, you might want one of those processes to read a file, but not the others. The same is true of spawned processes. Another common attacker tactic is to try to spawn a shell in a container. That's why there's this big drive of distro lists these days do not have shells at all. Sometimes you still need them, sometimes they're still there, attackers can still get them. And lastly, the ugliest, sometimes you just mount the host's etc. It happens, it's terrible, but I've seen it. And that's what I'm going to use as my example. So I'm going to make another test pod. Looks very similar to the last one, but now we've mounted the host's etc directory into the container under host etc. We need it for some configuration thing, something hideous that we need to do. So we're going to launch this pod, we're going to exec into it to get a shell, and then we're going to cat out the host password file. Probably not what was intended when this was set up. So how can we detect this? Well, Linux, as a Unix system, everything is a file, means there's lots of ways of interacting with files. So there are the classic open read and write syscalls, but there's a million other ways to do it. There are some specialized ones like copy file range. There is the async I/O stuff. There's IO-URing. There's even mmap, which is a fun one, which lets you pretend that a file is a piece of continuous memory to your process. These are all ways of interacting with files, and trying to instrument all of them sounds like a pain. Thankfully, we don't just have to instrument individual syscalls. We can instrument into and attach eBPF programs to other functions within the kernel. So in this case, we figured out that there are 3 that cover basically all ways of interacting with them. There is security file permission, which is called by basically everything. The security mmap file, which is used for memory mapping. And finally, security path truncate, which is used to handle some edge cases around being able to modify file contents if you truncate the file. So we can instrument those 3. So we're going to make another tracing policy. It's going to have 3 kprobes, 1 for each of those. So first, we're going to hook security file permission. And note that we only care about host etc. So we're going to filter for that in kernel, which means we only generate Tetragon events that are sent to the user space agent for Tetragon if it is a file name with that at the front, because of the prefix operator. And you can see that much like the one before, we're grabbing information about this, this file called a security file permission. Then we do something very similar for mmap, again, for those values, but different arguments because the arguments to this function are different. And then once again to security path truncate. So putting all of that together, we have another thing, and we're going to go and we're going to read that host etc password file again. And what do we see? Well, we see that the process starts, we see that it calls read twice on host etc password, and then exits, which is exactly what we wanted to see. We can observe that it has read a file, and we know which file it's read. If you're wondering why it calls it twice, by the way, if you run strace, the classic utility on cat, and you grep for only open and read events to see what's going on, and you ignore it doing some shared library stuff, you can see that it opens the password file and then reads it twice. Why cat does that, I have no idea. Go read its source code. But it does. But the point is that Tetragon found both of them, which is the interesting part. There are some pretty big limitations to this one. This works based on file name, which means if you can rename a file, or if you can make a hard link to a file, or something else that obscures the file name by the point it gets down to these functions, it can be missed. So that's a big limitation to be aware of. Yeah, that's the main thing. Right, what's next?
What's next? The next thing is Tetragon 1.0. So Tetragon at the moment is release 0.11, I believe. We are releasing 1.0 very, very, very soon, like expected any day at this point. So we wanted to ask you to try it out, to report as bugs if you find any, to contribute if you want. The Tetragon documentation is under tetragon.io. In the documentation, we have documented all the use cases we showed together and several more. They are documented in a way that you can follow them and reproduce them in your cluster. In the repository that is on GitHub under Cilium organization, we have also many, many examples of tracing policies so that you don't have to write them on your own. So please try them out. We are on Slack. On the Cilium Slack, we have Tetragon channel, so come talk to us there too. Yeah, and celebrate Tetragon 1.0 with us. Here we also put some other resources that you may want to check out. So tetragon.io is Tetragon documentation. eBPF.io is a website about eBPF. If you want to learn more, you will find a ton of resources there. Cilium.io is Cilium documentation, but one thing that is very interesting there is there are hands-on labs. Some of the hands-on labs also cover Tetragon. So if you want to try it out, but not in your cluster, then feel free to try out the Tetragon labs. And under isovalent.com, you can find information about isovalent, of course, but you can also download a few books, a few PDFs. One of them is the Learning eBPF book by Bliss Rice. If you want to learn more about eBPF and write your own code, then it's the best resource, honestly. And there's also a book about Tetragon specifically, security observability with eBPF. So check it out too. And with that, thank you very much for attending this talk. Do we have time for questions? Yeah? Okay.